cover is solving electric circuits and Kirchhoff's laws. Now, first of all, there are three things that we have to understand. Behavior of power supply. In our A1, we'll deal with voltage supply, that is a cell or a battery. Source of EMF, that is a cell or a battery. So a power supply, cell or battery, then we will understand the behavior of a resistor. That is also called a load. And then we will understand the behavior of nodes or junctions in a circuit. Now, first of all, what is the role of a battery for current? Let's suppose you have this battery and this is the positive terminal and this is the negative terminal. Three students have different opinion about the current through the battery, and just for example, you have to tell which one of them is right. So for example, a student states that current entering from the positive terminal was 5 ampere and the battery was of 2 volts. That's why it eats some current, and here the current is 3 ampere. Now, this is student number 1 who claims that the battery will change the current. You remember in your O level, you have studied that on a single path, the current remains same. So whether it's a resistor, a device, or a battery, the current entering will always be equal to the current leaving. Hence, this is wrong. So if the current entering the battery is 5 ampere, then current leaving the battery will also be 5 ampere. The second student who knows some electricity, he says that the current entering the battery will always be equal to the current leaving the battery. These two currents will always be equal. So the amount of current entering the battery will always be equal to the amount of current leaving the battery. This student says that a 5 ampere current enters from the positive terminal and a 5 ampere current leaves from the negative terminal. And there's another student. He says that I have a battery in which 5 ampere current enters from the negative terminal and 5 ampere current also leaves from the positive terminal. So for this student, the current is from the negative terminal towards the positive terminal. Now the student number 1, this student was wrong because he said the current would be different. The current should be same. These two students are right about the current because they both are saying that the current entering the battery will be equal to the current leaving the battery. However, the flow of current can be two-way. The current could be from positive to negative, or it could be from negative to positive. How is it possible? Sometimes the cells are being charged. When cells are being charged, the current is from positive to negative. So if current is entering from the positive terminal and leaving from the negative terminal, then the cell is being charged. And in this example, when the current is from the negative terminal towards the positive terminal, the cell is being used. So this cell is being used. Now, if we proceed further, if current on the two sides of the battery is same, then current is basically charge per second or coulombs per second. Then what is changed for this charge? Basically, the amount of energy possessed by the charge entering the battery is different from the amount of energy possessed by the charge leaving the battery. Now let's suppose if you have a battery and this battery is of 2 volts. What this means? A battery of 2 volts means that it will exchange, this battery will exchange 2 joules of energy. This battery will exchange 2 joules of energy with every 1 coulomb of charge that passes through it. So when you have a battery of 2 volt, it will exchange 2 joules of energy with every 1 coulomb of charge that passes through it. Now the question is that this battery will give energy or it will take energy. It depends whether the charge is moving from negative terminal towards the positive terminal or positive terminal towards the negative terminal. The flow of current can be either from positive towards negative or negative towards positive. Let's suppose this cell is being used. When the cell is in use and it is delivering energy, the current enters from the negative terminal. Let's suppose the current entering the negative terminal was 3 ampere. Now, by principle, you know that if 3 ampere current enters the negative terminal, then the current leaving the positive terminal will also be 3 ampere. It cannot be different. Now, what is meant by 3 ampere? Actually, 3 ampere is 3 coulombs of charge passing through a point in 1 second. So you have 3 coulombs of charge passing through this cell in 1 second. That's why the current is 3 ampere. And initial energy of this 3 coulomb charge could be anything. It depends on the circuit in which this cell is connected. Now, let's suppose, just for example, every 1 coulomb charge has an energy of, let's suppose here it has 3 joules of energy. So every 1 coulomb charge has 3 joules of energy. Now, if this is point A, this point A would be at 3 volt because the charge passing through A has 3 joule of energy for every 1 coulomb. So energy possessed by every 1 coulomb charge is the volts. Point A is at 3 volts. That's why every 1 coulomb charge passing through A has 3 joules of energy. Now you see this 3 ampere current is moving from negative terminal towards the positive terminal. So negative terminal is low potential terminal. Positive terminal is high potential terminal. So the charge is moving towards high potential terminal. So when the charge moves towards the high potential terminal, it is same as a mass is moving towards height. So when objects move towards height, they gain energy. So when this charge moves from low potential terminal towards the high potential terminal, it will gain electrical potential energy or electrical energy. Initially, its energy was 3 joules. After passing through the cell is of 2 volts. It exchanges 2 joules of energy. So the charge will gain 2 joule of energy from the cell. And here, this 1 coulomb charge, every 1 coulomb charge, 3 ampere means 3 coulomb in every second. No, if 3 coulomb charge is entering the cell in every coulomb, in every second, then 3 coulomb of charge is leaving the cell in every second. However, when the charge leaves this cell, its energy would become, you see, every 1 coulomb after leaving the cell, it will have 3 joule plus 2 joule. From where this 2 joule is coming from the cell. So this energy would become 5 joules. So this charge after passing through the cell will have 5 joule of energy. And as a result, if this is point B, this point B will be at 5 volt. Since when the charges are passing through this point B, they have 5 joule of energy each. Initially, their energy was, you see, 3 joule. And 2 joules are given by the cell. So after passing through the cell, it becomes 5 joule. As a result, point B is at 5 volt. Now this cell is in use. Now let's see another example. in which we have a battery and the current is passing through this battery from the positive terminal towards the negative terminal. Let's suppose we have a current of 2 ampere. What this means, we have 2 coulomb charge. We have 2 coulomb charge in every 1 second. So we have 2 coulomb charge in every 1 second. And let's suppose this is a cell of 5 volt. What this means, this cell can exchange 5 joules of energy with every coulomb charge passing through it. Now this cell is of 5 volts. Every 1 coulomb has, let's suppose here, it has 2 joules of energy. Now, if the charge that is entering the cell has 2 joules of energy for every 1 coulomb, then if this is point, just for example, if we have this point A, then this point A is at 2 volt. Since the charge passing through A has an energy of 2 joules, so this point A is at 2 volts. Now this current of 2 ampere is moving from the positive terminal towards the negative terminal. So when the current is moving from high potential to low potential, the charges will lose energy. So it is moving towards depth. From high potential towards the low potential, energy will be lost by the charge. Now initially the charge has 2 joules of energy. It will lose an energy of 5 joules. Now you can ask a question. How is it possible for a charge that has 2 joules of energy to lose 5 joules? How can the lost energy be greater than the energy possessed? Basically, this 2 joule is with respect to a reference that is 0 volt. Basically, this 2 volt is with respect to a reference that is 0 volt, and this reference is relative. Now, what this means? It means that this 0 volt is human defined. So this is not absolute, but it is a defined value. When this 0 volt is a defined value, then this 2 volt could be anything. It could be 100 volt, 110 volt, or any value. So one thing, we are not going to discuss this in detail. One thing is that for electricity, the volts are relative. They are not absolute. So when something is relative, the amount possessed can be less than the amount delivered. Just for example, if a charge possesses 2 volt, those 2 volts are relative. A charge possessing 2 volt is capable of delivering billions of volts. So the possession is not important. The initial amount that a charge has is not important. It depends on the reference. If you change the reference, the initial volts are changed. So just ignore that. No, the basic point is at point A, we have 2 volt. The current is 2 ampere. It is moving from positive terminal towards the negative terminal. We are moving from high potential to low potential. The charge will lose energy. One thing, if the current entering the battery is 2 ampere, then the current leaving the battery will still be 2 ampere. So we have 2 coulomb of charge passing through the battery in 1 second. What is changed? Basically, the battery will take 5 joule from every coulomb. Since we are moving from positive to negative, the charge will lose 5 joules of energy. As a result, the energy remaining with the charge will be, initial energy was 5 joule, energy lost is, initial energy was 2 joules, energy lost is 5 joules. As a result, the remaining energy is negative 3 joule. So after passing through the cell, every charge has an energy of negative 3 joule. What is meant by this negative 3 joule? It means that the charge after passing the cell has 3 joules less than the reference. This 0 volt is the reference. So we take some value or some charge as a reference and we define it as 0. Just for example, if the reference value is 100, that 100 will be called as 0. Then this 2 would be 102 and negative 3 would be 97. We need to understand that. Just for example, let's suppose we have a reference and we have some relative potential, and then we have, just for example, actual potential. Let's understand this concept, the concept of negative and positive volts. Just for example, if we take 100 joule per coulomb as a reference, if we take a charge that is at 100 joule per coulomb as 0 volt, then this 0 volt is basically this 100 volt. Now, if you have a relative potential of, let's suppose, 5 volt, what this means? It means that this 5 volt is bigger than the reference, which is 0 volt. Hence, it is actually 105 volts. Now, let's suppose if you take 1000 joule per coulomb as reference, then 1000 will represent 0. If you take 1000 joule per coulomb as reference, then 1000 volt will represent 0 volt. It's like when you define your height and you are at some floor of the building and you say my height is 6 feet, just for example, then you are measuring your height with respect to your floor. And any floor on which you are, just for example, if we have a person which is on this floor, for him, this floor is at 0 height. This 0 height is with respect to this person. We take this person. For this person, he will say this floor is at 0 height. If we take another person which is at this floor, for him, this would be 0. Now, all these zeros are relative, and the heights which we are measuring are relative, and relative values are with respect to our reference. Now, if you say this 1000 joule per coulomb, a charge has 1000 volt, and this 1000 volt is taken as earth or reference, then this 1000 volt will represent 0 volt, and a relative potential of 10 volt will be actually 1010 volts. Now, if in a system you say a charge that has 5 joule per coulomb is reference, then this 5 volt is your reference. You're saying that 5 volt is defined as 0 volt, then what would be 1 volt? 1 volt will represent 6 volt. So all the volts that we determine, they are with respect to our reference. That's why we can have a negative potential and a positive potential. Now, just for example, in this example, initially we have 2 volt, 5 volt are taken by the cell, and the remaining volts are obviously 2 minus 5, they are minus 3 volt. Now, two things that we have understood are, for a cell can take energy or it can give energy. The summary of all this concept is we can have flow of current through the cell from the positive terminal towards the negative terminal, or from the negative terminal towards the positive terminal. Just for example, if you have 10 volt at this point, let's suppose this point is point A. This is point P, it is at 10 volt. Now you have a current of 5 ampere, you have a current of 5 ampere. One thing that is common between these two currents, the current from A and the current from P, they both have one thing common. That is, every 1 coulomb charge has 10 joules of energy. Here, every 1 coulomb charge has 10 joules of energy. Here, every 1 coulomb charge has 10 joules of energy. The only, no, let's suppose here the current is not from this point, but it is from this side. This point is A, and the current is 5 ampere. Now, one thing is common. The current of 5 ampere here has 10 joule per coulomb because point P is at 10 volts. And this point A is also at 10 volts. And all the potentials in electricity are relative. These 10 volts are with respect to some 0 volt. Now this 10 volt, this 10 volt, and this 10 volt. 10 volt at P and 10 volt at A could be different. If they are two different circuits, then they could have some different references, and these 10 volts in the two circuits could have different meaning. However, for an individual circuit, if this charge is moving from point P and point P is at 10 volt, then this 5 ampere current will have an energy of 10 joule per coulomb. And here, this 5 ampere current, every 1 coulomb charge will have an energy of 10 joule per coulomb. Now let's suppose this is a cell of 1 volt. And this is a cell, this is the second cell. Just for example, this is cell E1 and this is cell E2. Cell E1 is of 1 volt. Cell E2 is also of 1 volt. What is the difference between the two situations? Through cell E1, the current is moving from the positive terminal towards the negative terminal. You can see that the current is moving from positive terminal towards the negative terminal, from high potential to low potential. When you move from high potential to low potential, the charges lose energy. 1 volt will be lost. 1 joule per coulomb will be lost. And if you have a point B here, basically potential at point B would become VB is equal to, initially you see it was 10 volt. You're moving from high to low, positive to negative. The charge will lose energy. How much energy is lost? 1 joule per coulomb or 1 volt. So the remaining energy would become 10 volt minus 1 volt. So the answer would become 9 volt. So at point B, you will get 9 volts. Now in the second cell, E2. In E2, you also have 5 ampere of current. 5 ampere of current means that 5 coulomb of charge is passing through the cell in every second. And every 1 coulomb charge has an energy of, in total it is 5 coulomb, and every 1 coulomb has an energy of 10 joule. Now this is moving from the negative terminal towards the positive terminal. The flow of current is from the negative terminal towards the positive terminal. When you go from negative to positive, you're moving towards height. So the volts are gained by the charge. The charge will gain energy. So this charge will gain energy. Initial volts are 10 volts and the cell will deliver 1 extra volt. So if you have a point Q here, the volts at point Q would become 10 plus 1, so it would become 11 volts. So point Q will have 11 volts since 1 volt is delivered by this cell. So this is the concept of a cell. Current entering the cell will always be equal to the current leaving the cell, and the cell could gain energy or it could lose energy. If the charge is gaining energy, then the cell is losing energy. When the charge moves from positive towards negative, then the charge will lose energy and the cell will gain energy. In this example, the cell is being charged. While in the second example, this cell is being used. So when the charge is gaining energy, the cell is losing energy and the cell is being used. This was the concept of cell. Now what about the resistors? Resistors have same concepts. However, the sign in cell is built in, while for resistors, the signs are decided by the current. Just for example, if we have this resistor R1 and this R1 has flow of current towards this side from left to right. If the current is towards right, then this is terminal A and this is terminal B. If current is from A to B, then A must be high potential terminal and B must be low potential terminal. So with respect to this current I, if we apply signs to this resistor, this A would be given a positive sign and this B would be given a negative sign, and current is always from positive towards negative. Now let's suppose we have another resistor. Just for example, this is resistor R2. This resistor R2 has a current I. Now current is from, this is terminal P, this is terminal Q. Current is from P to Q. So as a result, this would become positive, this would become negative, because current is always from positive towards negative. So for battery, the signs are independent of the current. If you have current towards right, or you have current towards left, it will not affect the signs of the battery. So the negative and positive of the battery is built in and it is independent of the current. However, for resistors, current is always from positive terminal, high potential terminal towards the low potential terminal. Now, how will you calculate the potentials on the two sides of a single resistor? Just for example, let's solve an example. You have this resistor. Resistor is of 5 ohms. What this means, if you apply a potential difference of 5 volt, then you will get a current of 1 ampere for this resistor. Now let's suppose this is point B and this is point A. If you get a current of 1 ampere from A to B, it means that B is at low potential and A is at high potential. So one thing is clear, A is at high potential and B is at low potential. Now with respect to this current of 1 ampere, you can apply signs for this resistor. The side, just for example, this is point P and this is point Q. Current is from P to Q, so P would be positive and Q would be negative. Now, in this question, you are given with potential at B. Let's suppose potential at B is given as 6 volt. What this means? Every 1 coulomb charge that enters B, that passes through B, will have an energy of 6 joules. So every 1 coulomb charge that enters B or that passes B will have energy of 6 joules. So this 6 volt means that you will get an energy of 6 joules by a charge of 1 coulomb that is passing through B. Now the question is, what would be the potential at A? Now focus on one thing. B is given and A is missing. It is to be calculated. VA is to be calculated. Now you see, from B to A, if you are moving from B to A, then basically you are moving from the negative side towards the positive side. So what will happen is that this 1 ampere will be multiplied by 5 ohm according to Ohm's law. So V is equal to IR, it would become 5 volt. So 5 volt is across this resistor, which means that this resistor is taking 5 joules of energy from every 1 coulomb of charge. However, to solve this question, you are moving from point A, point B to point A because B is given and A is to be calculated. When you move from B to A, actually you are moving from negative side towards positive side. So from negative to positive, this 5 volt will be added. Since you are moving from low potential to high potential, so 5 volt will be added. So here you have 6 volt. This 6 volt plus this 5 volt will become 11 volt here. So here you will get a potential of 11 volt. Now by principle, if you have a resistor or a battery, one thing is clear. If you are moving from positive towards negative, if you are given with volts on the positive side, just for example, you have 10 volts on the positive side, this resistor is consuming 2 volts. What would be the volts on negative side? It would be 10 minus 2, it would be 8 volts. And if you are given with volts on the negative side, then just for example, this is negative side, this is positive side. How will you decide this positive and negative with respect to the flow of current? So current will decide the positive and negative of the resistor. And for a battery, the positive and negative is built in. Now let's suppose on the negative side, you have 10 volt. And this resistor is also consuming 2 volt. Potential difference across the resistor is 2 volt, which means that 2 joule of energy is converted to heat for every 1 coulomb of charge passing through this resistor. Now 10 volt is the starting potential and you're moving from negative to positive. When you move from negative side towards the positive side, the volts are basically added. So you have 10 volt here and this 2 volt, since you are moving from the negative side towards the positive side, low potential to high potential will be added up. So it would become 10 volt plus 2 volt. So it is 12 volt. So this is the principle. Now let's solve an example that contains a battery and some resistors. Just for example, we have one branch of a circuit in which you have this battery and then you have this resistor and these are 2 points. Now let's suppose this is one branch taken from a whole circuit. This is point A, this is point B. Let's suppose you have 50 volts at A. Potential at B is not given. Hence, the flow of current can be towards right or it could be towards left, depending on the values in the circuit. Potential at B is missing. Now, let's suppose this is cell E1. Cell E1 has a potential difference of 10 volt and EMF of 10 volt. And we are ignoring the losses inside this cell. It has no internal resistance. Now, this resistor, just for example, it is of 10 ohm. And let's suppose you have a current of 2 ampere in this direction. One thing, signs of battery are independent of the current, and the signs of the resistor will depend on the current. Now let's suppose here you have another point C. Potential at C is also missing. Now it's one path circuit, so current throughout this circuit, throughout this branch would be same. It is 2 ampere throughout. Now you see, this is 2 ampere, this is 10 ohm, so you have 20 volts across this resistor. Now let's calculate VC. To calculate VC, you have to focus on one thing. What is given and what is to be calculated. Potential at B is missing. You have potential at A. Potential at A is 50 volts and the battery is of 10 volts and this battery is E1. What would be the potential at point C? Potential at point C would be since you're moving from high potential to low potential. Positive is high potential, negative is low potential. So this 10 volt will be subtracted. So whenever you move from positive side towards negative side, the volts will be subtracted. What will you get at point C? It would be 50 volt minus 10 volt, that is eaten up by the battery, and the remaining one would be 40 volt. Now VC is at 40 volt. What is the reason for that? Point A is at high potential, point C is at low potential. So when you move from A to C, the volts are subtracted. Now at point C, you have 40 volts because the 10 volts are taken by the cell. Now apply signs to this resistor. Flow of current is towards right. So this side would be positive. Current will be from positive towards negative. So in the resistor, current is from left to right. So left side would be positive and right side would be negative. Now positive is high potential and negative is low potential. At point C, you have 40 volts and the resistor is consuming 20 volts. And you are moving from positive side towards negative side, high potential to low potential. So this is 40 volt. These 20 volts will be subtracted. What would you get at point B is, it is 40 volt and minus, since you are moving from positive towards negative, so it would be 40 volt minus 20 volt and the answer would be 20 volt. By this method, you can calculate missing potentials at given points. Now let's solve another example like this to clear this concept. Let's suppose you have this battery, then you have this resistor, then you have another battery, then you have another resistor, then you have another battery. Now let's solve this circuit. Let's suppose current in this given branch, this is a branch taken from the whole circuit, and let's suppose this is point A and this is point B. Now in your O level, you have studied that current only flows through the complete circuit. For one thing, in your O level in electrostatics, you have studied that when a charged conductor is connected to earth, there is a flow of current. Electrons can flow from the conductor to the earth or from the earth to the conductor. So basically, a closed loop is not compulsory. You must have a complete path between 2 points having a different potential. Just for example, if VA, potential at A, is not equal to potential at B, then A and B have a potential difference. If you have a potential difference and a complete path, you have a current. Now, current will depend on the batteries and potentials of A and B. Let's suppose in this given example, the current is already given. Let's suppose this current is, we are understanding the circuit solving. Current is already given. It is given by the examiner. So you have to accept the current that is given by the examiner. Let's suppose the examiner gives a current of 1 ampere throughout this circuit. from B to A. Now, one thing, this is a cell of 2 volt. This is a resistor of 1 ohm. This is a cell of 3 volt. This is a cell of, just for example, 5 volt. And this is also a resistor of 1 ohm. So if you have a current of 1 ampere and a resistor of 1 ohm, then the potential difference across the resistor will be 1 ohm into 1 ampere. It would become 1 volt. So this resistor consumes a potential, it has a potential difference of 1 volt. This resistor also have a potential difference of 1 ampere into 1 ohm. So it would become 1 volt. Now you see, if you follow the direction of current, what would be the signs of resistors? Through this resistor, current is from left to right. So this side would become positive and this side would become negative. Current is from positive towards negative. Now in this resistor, the current enters from this side and it leaves from this side. So current is always from positive towards negative through a resistor. So this is positive terminal and this is negative terminal. Signs of batteries are independent of the resistors. This terminal is negative, this terminal is positive. For this battery, this terminal is negative and this terminal is positive. For this battery, this is positive terminal and this is negative terminal. Now let's calculate the potentials of points from one given potential. Just for example, examiner states that potential at A is, let's suppose, 100 volt. And they ask you what is potential at point C, what is potential at point D, what is potential at this point E, what is potential at this point F, and what is potential at this point B. Now, basically, you have to move from given towards missing, and you have to observe the signs. If you are moving from positive towards negative, if you're moving from positive towards negative, if given is on the positive side and to be calculated is on the negative side, then you have to subtract, and vice versa. If given is on negative side and what you have to calculate is on positive side, then you have to add. So if you move from negative to positive, you have to add. If you move from positive to negative, then you have to subtract. Now you see, point A is on positive side and point C is on negative side. Point C is on negative side. As a result, point A is at 100 volts. What would be the potential at point C? Now you're moving from positive towards negative, so you have to subtract. So it would become 100 volt minus 2 volt. So the answer would be, here you will get 98 volts. So this would be 98 volts. Now you see, point C is at 98 volts. And you're moving from negative towards positive. So you have to add it. So this 1 volt, this 1 volt potential difference across this 1 ohm will be added. So 98 volt, that was initial. You're moving from negative towards positive. This 1 volt will be added. And at D, you will get 99 volts. So potential at D is 99 volts. Now let's move on. Now you see, this terminal is negative and this terminal is positive for 3 volt battery. You are moving from negative towards positive. You are moving from negative towards positive. So you have to add. This 3 volt will be added. So what you will get is 99 plus 3. So it would become 102 volts. Here at E, you have 102 volts. Now you see, this resistor of that is consuming 1 volt. This resistor that is consuming 1 volt, you are moving from negative side towards positive side. When you move from E to F, E is on negative side and F is on positive side. So you're moving from negative towards positive. So this 1 volt will be added. So it would become at point F, what you would get, it would become basically at point E, you have 102 volt. And this 1 volt across 1 ohm will be added because you are moving from negative terminal towards the positive terminal. Since you are moving from negative towards positive, so this 1 volt will be added. And here you will get 102 plus 1. So it would become 103 volt. Now you have to move from F to B. In moving from F to B, you see this is battery of 5 volt. This is a battery of 5 volt, and here you have 103 volt. This 5 volt, since you are moving from positive towards negative, so this 5 volt will be subtracted. Here you will get 103 minus 5, it would become 98 volts. So at point B, you will get 98 volts. So this was a branch in a circuit. This was a branch in a circuit that we have solved using the concepts that we studied. So today we have to study up to this point. In the next class, we'll start from here and then we'll move towards Kirchhoff's laws.